This conference will now be recorded.
Hello everyone, we'll start with oxides and oxoanions of transition metals and also some other reagents that are very important in this chapter. So transition metals, it can have different types of oxidation state, and when we have different oxides and oxoanions, then we will see that different types of oxidation states that are also present. Now, when the metal it is in intermediate oxidation state, that means suppose a particular metal it can have oxidation state +2, +3, +4, +5, then +3, +4, these two are intermediate oxidation state. That is, it is not very high, it is not very low. So when this is the condition, that is oxidation state, it is intermediate, then what happens? The corresponding oxide, its nature will be amphoteric. And if oxidation state is very high, it will have acidic in nature. If oxidation state is very low, it will have basic nature. Okay, so low oxidation state, basic, intermediate, it is amphoteric, and when it is high oxidation state, it will be acidic. Now for manganese, this is the one of the oxide, Mn2O7. Now in Mn2O7, oxidation state is +7. Okay, we know that manganese it can have different types of oxidation state, and here we have 5 examples. See, MnO where oxidation state is +2, then another type of oxide Mn2O3 where oxidation state +3, Mn3O4 here we have oxidation state 8 divided by 3, then MnO2 +4 and +7 Mn2O7. Now see, these two are basic in nature because here oxidation state towards lower side, but +7 that is very high, so that is why it is acidic, and 8 by 3 and +4 these two are intermediate, so that is why they are amphoteric in nature. This manganese oxide Mn2O7, when it is dissolving in water, the corresponding acid that you will get, that is known as permanganic acid, and the formula HMnO4. So as it is acidic oxide, so obviously after dissolving in water, it will give us permanganic acid. CrO3. Here oxidation state for chromium is +6 because 3 oxygen and each oxygen is carrying -2. So total negative charge, total positive charge, it has to be +6. So that is the oxidation state of chromium is +6. This is also very high oxidation state for chromium. Okay, highest oxidation state. So that is why this oxide, when you are dissolving it in water, just like Mn2O7, it is giving us this acid, and from CrO3 we will get this type of acid, that is H2CrO4. Another acid is dichromic acid, H2Cr2O7. Another oxide of chromium, which is Cr2O3, where oxidation state of chromium is +3. And although it is insoluble in water, but it dissolves in acid. Now in CrO3 oxidation state is +6, and in Cr2O3 oxidation state is low compared to +6 because now it is +3. So when it is not soluble in water, insoluble, but Cr2O3 as it is having lower oxidation state, that means it will have basic character, and that is the reason now it is soluble in acid. And what it gives after dissolving in acid, we get chromium hexa H2O, that is 6 water molecules surrounding chromium 3+. So H2O is neutral ligand, so that is why whatever is the oxidation state, directly you can see outside this third bracket we have 3+ charge. These hydrated chromium ions that we are getting after dissolving in acid, now it can react with base also, and ultimately it is giving HO6. So see, here we have total 6 water, but when it is treated with base will capture this H from H2O. So from H2O now we will get hydroxy ion HO-. So that is why here the formula is chromium HO6 3-. It dissolves in concentrated alkali to yield chromite ions. That means Cr2O3, when it is dissolved in concentrated alkali, it will give CrO2 minus. Now each oxygen is -2, so total negative charge here is -4. Outside one negative charge extra, that means here oxidation state it is still +3. Okay. So Mn2O7 reacting with water, it is giving us the acid HMnO4, and the formula of this molecule, which is permanganic acid, that is also given. And the two formulas here we have H2CrO4, which is chromic acid, and H2Cr2O7, which is dichromic acid. So this is H2CrO4 and this is H2Cr2O7. Fine. And CrO3, when you are dissolving it in water, what you are getting? You are getting chromic acid, H2CrO4. Okay, which is already mentioned here that CrO3, it is giving us chromic acid, H2CrO4, when it is dissolved in water. Just from Mn2O7 we are getting HMnO4. Just like that, when it is CrO3, we are getting H2CrO4. So when it is manganese 2 plus oxidation state, for example, manganese this oxide MnO, see the color is like this, it is very pale. Mn +3 oxidation state, example is Mn2O3, and Mn +4 oxidation state, which is MnO2, then Mn +6 oxidation state, which you can find in MnO4 2 minus, and Mn +7 oxidation state, which is found in MnO4 minus. So here gradually the oxidation state is increasing from +2, then +3, +4, +5, +7, 4, then 6, then 7. And as we are moving from left to right, number of d electrons are also changing. Gradually it is becoming less and less. So when it is +7, there is no d electron. And also the nature, that is whether it will be basic, amphoteric or acidic, that also we can understand, because when you are moving from lower oxidation state to higher oxidation state, gradually the nature is changing: basic, amphoteric, acidic. Okay, and as the number of d electrons are changing, so the color is also dependent on that, because the color, it is when there is d electrons present, it is because of dd transition. Okay, and as the number of d electrons are changing, color will also change. And for the last case, that is MnO4 minus, where oxidation state is +7, here we do not have any d electron. So here the color that you are seeing, that is not for dd transition, it is because of charge transfer from the ligand towards the metal. Okay, so here ligand is basically oxide and metal is manganese. So here the generation of color is not for dd transition, but for charge transfer from ligand to metal. So in this slide, is there any doubt? Should I repeat any part? Now in the previous slide we have seen only oxides, but there is another term which is oxoanion. Now oxide is simple, it is just the metal and oxide, that is oxygen atom will be present. But when it is oxoanion, then also the metal is present, oxygen is present, but overall there will be negative charge. So that is why the term is oxoanion. Similarly, if there is overall positive charge, then the term will be oxocation. And oxides are basically neutral, so that is why we are not saying it is anion or cation. So three different things can happen. One is oxide, which is neutral. Oxoanion, this is carrying negative charge, that is why we are saying anion. And third possibility, oxocation, which is carrying positive charge. Now see here we have different cation, anion and oxides of the metal vanadium. In case of vanadium, the oxide V2O3, where oxidation state of vanadium is +3, it is basic in nature. Then another oxide which is V2O4, where oxidation state is now +4. This is less basic. Why? Because it is easy to understand. You are moving from +3 to +4. That means oxidation state is increased. So obviously now it will be less basic compared to V2O3. And the next oxide, which is V2O5, here oxidation state is +5, and this is amphoteric. So see how the nature is changing. When you are moving from V2O3 to V2O4 to V2O5, gradually it is becoming basic to less basic to amphoteric. But it may be sometimes acting as predominantly acidic, because amphoteric means what? It can behave both as basic as well as acidic, but it is predominantly acidic. How we will understand that V2O5 is predominantly acidic? See, V2O5 reacts with alkalis because it is acidic in nature, and it produces this type of oxoanion. So see, this is the example. V is vanadium. It is the short form of vanadium. Okay. Remember the first series in D block, which is starting from scandium, having formula Hc, and it is ending at zinc. Okay. So after scandium, the next element is vanadium, which is V, and atomic number for scandium is 21. So the next element atomic number is 22. Is there any doubt anymore? Can I continue? Is it okay? What is V? So V2O5. Yes? Clear? Reacts with alkalis, it produces the oxoanion VO4 3-. So this is the example of oxoanion because it is carrying 3 negative charge. So it produces this type of oxoanion salt, and it also reacts with acid because it is amphoteric in nature. So it can react with alkalis, then it will behave as if it is acidic. It can also react with acid. In that case, it will behave as if it is basic. That is the nature of amphoteric substance. It can be react with both alkalis and acid. So when V2O5 is reacting with alkali, it is producing VO4 3-. And look at this first equation, number 1. V2O5 reacting with alkali NaOH, it is producing this type of salt, Na3VO4. It is not balanced, but that is not important. Just focus on the product. What type of product you are getting? When V2O5 reacting with alkali, you are getting Na3VO4. So 3 sodium ion present. That means if you remove this 3 sodium, the anion that you will get VO4 3-, because this 3 negative charge balanced by 3 Na+. So this is the oxoanion you are getting when V2O5 reacting with NaOH. And in the second equation, V2O5 is also reacting with acid HNO3, nitric acid. And now what we are getting? We are getting VO2NO3. Now NO3, we know nitrate, it has single negative charge, -1. That means the positive charge that will be present over VO2, that will be +1. So here the oxocation that you are getting is VO2 +1. Okay. So when it reacts with acid, you are getting oxocation VO2 plus. Fine. Another reaction, V2O5 can also react with HCl, water, and what we are getting? We are getting VO H2O whole 5 2 plus. So another type of oxocation we are getting. When it is reacting with HNO3, we are getting VO2 single positive charge. And when it is reacting with HCl, now what we are getting? We are getting VO 2 plus charge, and 5 water molecules are surrounding it. So this VO2 plus oxocation, you can also look at the structure. V attached with oxygen with double bond, and total 5 water molecules are surrounding it. So how many, what is the coordination number here? Coordination number is 6, because you have total 5 H2O and 1 oxygen. So it will have octahedral type of shape. Outside the charge is mentioned, which is 2 plus. Here we also have the structure of V2O5. Okay, and this is VO4 3 negative charge. Okay, the structures of this oxocation, oxoanion, all these are given. V2O4, another oxide, it is when dissolved in acid also forms VO2 plus type of salt. So 2 plus, that is double positive charge. Okay, so different types of oxocations, examples you can see here. VO2 single positive charge, here oxidation state of vanadium is +5, and it is very easy to understand how it is +5, because you have total 2 oxygen. 2 oxygen means total negative charge -4. So vanadium, it must have +5 oxidation state, because +5 and 4 negative charge. That means 1 positive charge excess, which is outside the coordination sphere. So VO2 plus, in this oxocation, the oxidation state of vanadium is +5. And this is yellow in color. Another oxocation, which is 1 vanadium atom, 1 oxygen atom, but 2 positive charge. Now here the oxidation state of vanadium is +4. Okay, and if you have any problem to understand how we are getting the oxidation state, just use that formula, that is not formula actually, the calculation VO. So suppose oxidation state of vanadium is X. So it is X, 1 oxygen, that means -2 charge for each oxygen. Overall charge is +2. So if you use this type of equation, you can easily find out what is the value of X. So here X is -2. So it will be, when it is in the right hand side, it will be total +4 charge. And this oxocation is blue in color. So here we have this oxocation solution VO plus, which is yellow in color. Here oxidation state is +5, and VO 2 positive charge, where oxidation state of vanadium is +4. It is blue in color. Some more oxidation state of vanadium are also mentioned. V3 plus. Now the color is also blue, but it is different types of blue. And V2 plus, this is towards purple color. Okay. Here we have another example, titanium, scandium. Next element is vanadium. Third element is titanium. Okay. So for titanium, if you consider this type of oxocation, Ti, 1 oxygen, 2 positive charge. Here oxidation state of titanium is +4. Okay. So these are some examples of oxocation, and when oxidation state is changing, color of the solution, that is also changing. In this slide, any doubt?
No, ma'am.
So different types of oxides we have seen, and based on these different types of oxide, we have a problem here. Which of the following is amphoteric oxide? Here we have total 6 oxides, right? We have Mn2O7, then chromium O3, and Cr2O3. 2 different types of oxides of chromium we have. Okay, total 3 types, not 2 types. And 2 vanadium oxide. 3 chromium, 2 vanadium, 1 manganese. Okay, so we have to find which combination, that is different combination you have, option 1, 2, 3, 4, because in each option you have total 2 oxide. So what we have to do, we have to find out that option in which both the oxides will be amphoteric in nature. It may be that in any option, if you are finding that one of the oxide is amphoteric, another one is acidic or basic, then that is not the correct option. Both the oxide must be amphoteric, then only it will be the correct option. Okay. Now we know that when oxidation state increases, then acidity increases. Okay, that means if suppose for any particular metal, if you have 4 to 5 different types of oxidation state, then the oxidation state that are intermediate position, they will be considered as amphoteric. V2O4 here oxidation state of vanadium is, can you tell me what is the oxidation state of vanadium in V2O4? We have just discussed different oxides of vanadium, right? What is the oxidation state of vanadium in V2O4? That is the question. This molecule is neutral in nature and you have 4 oxygen atom, 2 vanadium. So overall neutral means what? Suppose if the oxidation state is X for vanadium and you have 2 vanadium, so it will be 2X. Total 4 oxygen, that means 4 into -2. Each oxygen is -2. Overall the molecule is neutral, so that is why I have written here 0. So from this equation you can understand, yes, it is +4. So +4 for vanadium, and for chromium it is +3. So basically first you have to write all the oxidation state, because when you will look at the oxidation state, you will be able to understand whether it is amphoteric, acidic or basic. So for vanadium, we know that oxidation state that is the possible oxidation states are +2, +3, +4, +5. So this is you can say that this is intermediate, right? Then chromium +3, but chromium can also have +6 oxidation state. That means it is towards lower side. In the second option, can you tell me the oxidation state of manganese in Mn2O7? Use this type of equation, you can easily find out the answer. Here all the molecules are neutral, so it will always be, that is in this equation, it will always be equal to 0. Yes, it is +7, and chromium 3 plus, it is +6. Chromium O, that means yes, +6. CrO 1 oxygen, that means it will be +2. Again we have V2O5, sorry, V2O5, it is first time we are getting here, it is +5, +5, +4. Now if you look at option 2, both are having very high oxidation state, because +7 is the highest oxidation state of Mn, +6 is the highest oxidation state of chromium. So it is very, we can easily understand that option 2 cannot be the correct option, because option 2 is carrying very high oxidation state. So both these will be acidic oxide. Okay. Then CrO, oxidation state of chromium is towards very low value, +2, which is the lowest oxidation state. So it will be basic character. And V2O5 vanadium is having a very high oxidation state, so it will be acidic. So option 3 is also not correct. And in option 4, again V2O5, where oxidation state of vanadium is maximum. So this is also towards higher oxidation state. Not just higher, it is the maximum oxidation state that is possible for vanadium. So this is also not correct. So only option left is the first option. Now this table I have already used probably in the last class, but if you look at this table, it will have give us clear idea that all these oxides, what is their nature. So vanadium oxide, that is V2O5, it is acidic. It has to be acidic because it is having highest oxidation state. VO2, it is amphoteric. Here oxidation state is +4, and if you consider the dimeric form, it will be V2O4. So V2O4 is amphoteric. Then if you consider the next metal, which is chromium, +2 basic, +3 amphoteric. This is +4, this is also amphoteric. That means Cr2O3, that will also be amphoteric. So in option 1, V2O4 and Cr2O3, both these are amphoteric. And this will be the correct option because we have to find that option where both the oxide are amphoteric. And M and C, different oxidation oxides are there. This is the lower oxidation state, so that is, it is basic. This is also towards lower side, this is basic. But these two are amphoteric because here oxidation state is +8/3 and this is +4. But we have in our question Mn2O7, which is having maximum oxidation state, so this is acid. So correct option will be option 1. Any doubt?
No, ma'am.
We have to find incorrect statement among the following. 4 statement are there. Only one will be wrong because it is single choice answer. The first statement, VOSO4, vanadium, then oxygen, then sulfate ion. It is saying that it is a reducing agent. Now, how to understand whether it will be reducing agent? Reducing agent, it is possible only when vanadium is having some d electron. But if it is not having d electron, how it can? Second one, incorrect statement, Cr2O3. But Cr2O3 is amphoteric. This is correct. You have to find out incorrect statement, not correct statement. Cr2O3 is amphoteric oxide. This is correct statement. This is true.
Okay, ma'am.
Then VOSO4, how you will understand whether it is reducing agent or not? Here, VO is basically the oxocationic part because VO2 plus, this is oxocation, and SO4 2 minus. So overall the molecule is neutral. Now if it is VO2 plus, then oxidation state of vanadium, it will be +4 because +4, oxygen -2, overall 2 positive charge excess. Now when it is V4 plus, can you tell me how many d electrons will be present? Vanadium when neutral, I am writing the electronic configuration. It is after argon, it is 3d to 4s2. Sorry, it is 3d3. So when it is neutral, if this is the electronic configuration, then what will be the electronic configuration when it is +4 oxidation state? Total 3d electron, 2 4s electron. So if you are having +4 oxidation state, that means you are removing 4 electron. So if you are removing 4 electron, now it will be converted to 3d1. So it is having 1 electron. Now if it is acting as reducing agent, that is VOSO4, reducing agent means what? It will donate electron. Now after donating 1 electron, 3d1 will be converted to 3d0. Now 3D0 is stable configuration. Compared to 3D1, it is stable configuration. That means when it is switching from 3D1 to 3D0, then it is moving towards more stable state. So here electron donation, that will be facile process. So this statement is also true, that it is reducing agent, because it after donation of electron, now it is achieving the stable configuration. That is why it is reducing agent. Third statement, ruthenium tetroxide. Can you tell me what is the oxidation state of ruthenium in RuO4? Oxidation state of ruthenium. Overall, the molecule is neutral. Just use the formula that I have, not formula, the equation. That is, just consider ruthenium as if it is having oxidation state X, 4 oxygen atom. That means each oxygen is -2. 4 oxygen is -2 into 4. That is -8. Overall, the molecule is neutral. So the equation will be X plus 4 into -2 equal to 0. So what will be the value of X? X plus 4 into -2. Overall 0. So X is 8. Now this is very high oxidation state. That means it is, obviously it will be oxidizing agent. Oxidizing agent means which accepts electron. So plus-8 oxidation state, as it is very high oxidation state, that means it will have a tendency to accept electron from other species. So this oxide of ruthenium is actually oxidizing agent, and this is also true. Ruthenium is in the same group with iron. Iron is in the first transition series. The second transition series ruthenium, and just below ruthenium we have osmium. Now, if you know what is the electronic configuration for iron, it is 3d6-4s2. That means if you move towards the next element in the same group, it will be 4d6-5s2 for ruthenium. Now, plus-8 oxidation state means what? You are removing 8 electrons. 8 electrons removed means 6 plus 2. That means all the valence electrons are removed. So now it is achieving the configuration of argon, because just before it there is argon configuration. So after removal of 8 electrons, there is no more electron left in D, 4D, so that it can donate. That means it cannot act as reducing agent. It has to act as oxidizing agent. It will accept electron. So that is why this statement is also true. Now, all the 3 statements, that is 1, 2, 3, if they are correct, that means the last one must be incorrect. Now here, why the first 3 statements are correct, there is enough logic behind that, and that we have just discussed. But the last one, it is basically, see, it is memory based. If you do not have previous knowledge whether that is red color of ruby, it is because of cobalt or any other metal. If you do not know, then it is not possible for us to answer. But here you can use elimination process. That is, if you know the first 3 options are not correct, so even if you do not have any idea that what is the actual reason for the red color of ruby, then also you can understand that this is not correct, because the first 3 are correct. So it has to be false statement. Any doubt? But we have to know which metal is actually responsible for the red color of ruby, and this is chromium. So depending on the amount of chromium, the intensity of the red color, that is also changing. The more is the amount, stronger is the red color. But the red color, it is not because of cobalt. It is because of chromium. So that is why the last statement is actually the incorrect statement. And we have to find the incorrect statement. So that is this is the correct option. Any doubt? Should I repeat? Next important reagent, KMnO4. Here the transition metal that is present is manganese, right? KMnO4, manganese is the D block element. Potassium is also there, oxygen is also there. It is solid. So when it is in solid state, at a first glance it seems as if it is a black colored solid, but actually it is purple. And that you will be able to understand. Just you take a pinch of this KMnO4, and if you dissolve in water, it will be like this purple color. Okay. So the purple color is so intense, it appears as if it is black, but actually it is not black. Okay. How we can make it? Preparation of potassium permanganate. Potassium is K, and permanganate, this part is MnO4, single negative charge, because you have removed potassium, and potassium is carrying single positive charge. Okay. How we can make it? For its preparation, we take pyrolusite, which is ore of manganese. Now, what is ore? That we have already seen in the chapter of metallurgy. Ore is basically naturally obtained any compound from which you can extract that particular metal. Okay. Pyrolusite is nothing but MnO2. So here we will use MnO2 as the source of manganese. There are two steps. First we will see what is the first step. Then we will see the second step. The first step is step 1. Conversion of pyrolusite into potassium manganate. See, potassium manganate, it is not permanganate. When it is permanganate, the formula is KMnO4. But when we are saying potassium manganate, there is no par. Manganate, simply manganate. Then the molecule is actually K2MnO4. K2MnO4, different formula. And if you remove 2 potassium ion, MnO4 2 minus, that will be the anion like this. So when it is permanganate, it is MnO4 single negative charge. When it is manganate, it is MnO4 double negative charge. Finely powdered pyrolusite we will take, and we will fuse it with either potassium hydroxide or potassium carbonate. You can take any of these, either KOH or K2CO3. In presence of air, air is source of oxygen. Basically, we need some oxidizing agent, and air will play the role of that oxidizing agent. You can also use some other oxidizing agent. For example, you can use KNO3 instead of using air, or you can use potassium perchlorate, AClO3. That is also another type of oxidizing agent. So first here we will get potassium manganate, which is K2MnO4, and see, this is green color. MnO4 minus permanganate is purple color, but when it is MnO4 2 minus, it is green color, different color. Okay. Now we will see the reactions. We have taken pyrolusite ore. We are treating it with KOH because that is the reagent used for fusion purpose, and oxygen, which is basically coming from air, and this is the oxidizing agent. You are getting potassium manganate. Another method, that is, instead of using KOH, you can also use K2CO3. which is another fusing reagent, that is the reagent for fusion purpose, and oxygen, as it is already there, it is for oxidizing, to show oxidizing property. Okay. Now, instead of using oxygen, we can also use KNO3 and KClO3. Here we also have the picture for K2MnO4 solution, how it actually appears. See, the color is completely different. Here we have used KNO3 instead of using oxygen. And for fusion, we have taken KOH. Pyrolusite, it has to be there. It is common reaction partner that is present in all the 4 equations. So here 4 different equations are given. You can use any of these equations. So KOH for fusion, KNO3 for oxidizing agent. Then in the second equation, we have used KClO3 as oxidizing agent and KOH as we have used in the third equation. But the important thing is, in each reaction, you are getting potassium manganate, right? Now, after the first step, what is the second step? In the second step, the K2MnO4 that you have already prepared by using any of these 4 equations, you will treat it with water. That is, just mix this K2MnO4 with water, and then we will use some oxidation reaction so that we can convert it to KMnO4. Now, why we are calling it oxidation? Because here oxidation state is +6. But the reagent that we are trying to prepare, oxidation state is +7. So from +6 to +7, that means it is loss of electron, and loss of electron means it is oxidation. Fine. Now this oxidation you can do in 2 ways. You can do it chemically, or you can do it by electrolysis. First we will see how we can convert K2MnO4 to KMnO4 by some chemical reaction. So step 2, chemical oxidation. So for oxidizing agent, what we have used H2SO4, sulfuric acid, because we know sulfuric acid has oxidation property. Potassium manganate reacting with sulfuric acid, we are getting potassium permanganate, which is the actual compound we are trying to prepare. Some other byproducts are also there. But why we are calling it disproportionation? Because here oxidation state of manganese in K2MnO4 is +6. So disproportionation reaction means same element, it will be oxidized and reduced simultaneously. So that is why here we are calling this equation disproportionation, because manganese +6 oxidation state, now it is converted to +7. But there is another compound of manganese which is MnO2, her oxidation state is +4. So 2 different compounds of manganese is there. If you consider conversion of K2MnO4 to K2KMnO4, it is +6 to +7. So it is oxidation. But if you consider +6 to this one, now from +6 you are having +4. So this is gain of electron. So that is why it is reduction. So this type of reaction is known as disproportionation. But we are interested in this compound. Okay. Then you can also use, instead of using H2SO4, you can also use CO2 water, and here also it is converted to KMnO4. Another compound of manganese is also there, so that is why it is also disproportionation. In the third equation, now the oxidizing agent that we have used is chlorine. Okay, here K2MnO4, that is converted to KMnO4, and chlorine is converted to Cl minus, chloride. So chlorine is accepting electron, so that is why it is acting as oxidizing agent. But K2MnO4, that is acting as reducing agent because it has lost electron. Sorry, this is not disproportionation actually, because here you do not have another compound of KMnO4. You can simply consider these two reactions as if it is oxidation of K2MnO4 by chlorine, and in the fourth equation by ozone. So ozone is also oxidizing in nature, and K2MnO4 is again oxidized to KMnO4, and O3 is reduced to oxygen. This is reduction. That means O3 is itself acting as oxidizing agent, and it is accepting electron from K2MnO4. So that is why K2MnO4 is oxidized to KMnO4. Okay. So all the four equations, is it clear? But as we have mentioned that we can do this conversion of K2MnO4 to KMnO4 either chemically or electrolysis. So chemically, how we can do it, that we have already seen in this four equation ABCD. Now we will see how by electrolysis also you can do the oxidation. So we are calling this electrolysis as electrolytic oxidation, because after all it is oxidation. For manufacturing potassium permanganate commercially, method of electrolytic oxidation, it is preferred over the chemical oxidation. Okay. So what we do in this case, the manganate solution means K2MnO4 solution that you have already obtained in step 1. Remember, in step 1 we have used some pyrolusite, that is ore of manganese. We have used some oxidizing agent and fusion reagent, and by using all this we have already prepared K2MnO4 in step 1. In step 2 we have seen some methods of chemical oxidation, but now we are seeing how by electrolysis also we can do the same thing. Here the manganate solution that we have obtained in step 1, it will be electrolyzed between iron electrode, because we know when we do electrolysis we need some electrode. Okay. So what reactions are actually happening here? K2MnO4, when it will be dissociated, it will give cation K plus and anion MnO4 2 minus. And as it is electrolysis, water is also there, and from water you will get H plus and HO minus. Now we know that at anode oxidation takes place. So see, MnO4 2 minus, which is having oxidation state plus 6, it has lost one electron and it is converted to MnO4 minus. This is plus 7. At cathode, reduction occurs. H plus is accepting these 2 electron. That is, if you multiply the first equation with 2, then it will be also 2 electron. Okay? Accepting 2 electron, which is these 2 electrons are donated by MnO4 2 minus already at anode. Now these 2 electrons will be accepted by H plus, and ultimately it will be hydrogen gas. Thus, manganate ions are oxidized to permanganate at anode electrode, and hydrogen gas is also produced at the cathode, another electrode. So this is the that is half reactions that are occurring at anode at cathode. But if you consider the overall reaction, it is K2MnO4 reacting with water, and this is oxidation. So that is why it is written in this way. And what we are getting? We are getting KMnO4 and also KOH. Now see, here H plus is converted to H2, right? And K plus is there. HO minus is also there. So this K plus and HO minus together will make potassium hydroxide. Okay? Because this is nothing but K plus and HO minus. Any doubt? After oxidation is complete, the solution is filtered and evaporated under controlled condition so that we can get deep purple black crystal of potassium permanganate. Okay. And why we have done filter, that is filtration, because if there is KOH is also produced, which is byproduct, but KOH having better solubility compared to KMnO4 in water. So that is why compared to KOH, as it has more solubility, KMnO4 can remain in solid state. That is, if you are there is presence of enough KMnO4 in water, it will be remaining as insoluble. So that is why you can filter it. Okay. But see what is mentioned here, the solution is filtered and evaporated under controlled condition. Okay, that means it can also remain in the filtered part. So after filtration, the filtered part that you have obtained, if you evaporating it, that means water will be evaporated, the solid part will be remaining, which is the deep purple colored crystals of KMn. Any doubt? So overall, what is the preparation method? First step, we are using pyrolusite and oxidizing pyrolusite plus oxidizing agent plus another reagent which is for fusion purpose. In the first step, you are getting K2MnO4, and this K2MnO4, now you are oxidizing it to the ultimate desired compound, which is Kmn. And this oxidation you can do either by electrolysis or by using some oxidizing agent. Okay. After preparation method of KMnO4, now we will see its physical properties. It is violet crystalline solid that we have seen already. That is what is its color. In aqueous solution, you will be better able to understand what is the actual color. Melting point 240 degrees centigrade. It is soluble in water, but what is the solubility amount? That also it is mentioned here. 6.4 gram per 100 gram of water. This is a maximum limit. That is, beyond this limit you cannot dissolve it. Okay. And this is at 293 Kelvin, because we know that solubility is dependent on temperature. So whenever you are mentioning the solubility, as we have done here, 6.4 gram per 100 gram of water, you must mention the temperature also. It is not just soluble in water, it is also soluble in some organic solvents, C, acetone, pyridine, methanol, acetic acid. And because of this solubility in different types of organic solvent also, you will see that KMnO4 is also used in organic chemistry, especially for oxidation as oxidizing reagent. So as it is also soluble in some organic solvent, so that is why we can also use it in organic reactions. Okay. Readily soluble in inorganic solvent also. Inorganic solvent as well as organic solvent. Rich purple color is there if it is concentrated aqueous solution. So see, this is very concentrated aqueous solution. But if you dilute it, gradually you will see the color is becoming pale. So it is almost colorless. Okay. Here we have the structure of KMnO4. K plus is the cation, and rest of the part, which is basically MnO4 single negative charge, that is written in this way. Mn, 4 oxygen atoms attached with it, 4 sigma bond and 3 pi bond, right? 4 sigma bond, 3 pi. So 3 pi bond, 1, 2, 3. Now what is its structure? Though we have written it in this way, but what is actual geometry, that we have to know. This is ionic compound, so it is having crystal type of structure, and crystal structure, whenever we are mentioning, there must be, that is 7 crystal system. So it is one of these crystal system which is orthorhombic. So KMnO4, it is having crystal structure of orthorhombic type. Fine. And if you only focus on MnO4 unit, then this unit is tetrahedral geometry. Mn attached with 4 oxygen, so tetrahedral geometry is possible. But whenever we say tetrahedral geometry, the corresponding hybridization, can you tell me when it is tetrahedral geometry, what is the corresponding hybridization? Tetrahedral geometry, hybridization is sp3. Very good example is methane. Okay, but in this case there is some exception, because though it is tetrahedral, but the hybridization is not sp3. Though we know that it is the general observation of when it is tetrahedral geometry in any species, if you have, it is always sp3 hybridization, but not in this case. So what is why it is different, that we have to see. Here we have both the ions, though we are discussing potassium permanganate, but here we have both the anion, which is Mn. The first one is MnO4, 2 negative charge, and the second one is MnO4, single negative charge. So first one is potassium manganate, second one is potassium permanganate. Both are tetrahedral actually, and the hybridization is not sp3, but it is D3s. But how we are getting D3s? See, to understand this, first you will write what is the electronic configuration of manganese when it is neutral. It is 3d5-4s2. Okay, now 3d5-4s2 after argon configuration, obviously. So how many electrons are there? Total 7 electrons. Okay, and after 4s we know there is 4p. This is a ground state electronic configuration, but when it is excited state, one of the electron from S can be transferred to 4p. So see, one of the electron from 4s, this is 4s. Now it is transferred to 4p, and this is 3d. Now we know that pi bonds, when formed, the electrons that are used, that electrons are not involved in hybridization. So these 2 electron in D and 1 electron in P, that are not part of hybridization. These 3 electron in D and 1 electron from S, together it is having the D3s hybridization, and 4 orbitals are taking part. That means you will get after hybridization total 4 D3s, and each of these D3s are used for sigma bond formation. Total 4 sigma bond. All these are by D3s, and these 3 which are not taking part in hybridization, these 3 electron will be used as for pi bond formation. So here we have total 4 oxygen atom, which is using D3s orbital of manganese to make 4 sigma bond. All these are sigma, but oxygen will use its 2p orbital and this single electron for pi bond formation. So see, here we have 2p and 3d overlap, sidewise overlap. So total 2 into 2p, 3d. 2p is for oxygen, 3d is for manganese. But 1 electron is also present in p. So that is why it is 1 into 2p pi, which is for oxygen, and this is for manganese. So now why we are focusing on this part, so that is discussing in detail, it is because it can be asked that among these 3 pi bonds, how many are 2p 3d type and how many are 2p 4p type. Then your answer will be, among these 3 pi bonds, 2 are 2p 3d type, another, the last one is 2p 4p type. So different types of pi bonds are there. So that is why it is important as to know the details of the hybridization, and why it is not sp3, why it is D3s. That is also clear here. because when 3D is used for hybridization, it is having lower energy compared to 4p. So that is why d orbital is used and 4s is used for hybridization. So it is not sp3, it is d3s, and this is exception. Okay. So regarding all the slides into this class, is there any doubt? So as there is no doubt, we are ending the session here.